Welcome everyone to today's central exercise session. We'll be discussing sheet number 7 today. Before we do that, just a very quick announcement on the examination. I'll have more details on that probably next week, and I'll also put up all the details on the Moodle page so you can read up on that. Just that you have all the current developments. I have finally gotten feedback from the examination office. So this is the official announcement of the form of the end term. As in the last semester, we will do the end term as a one-time remote exercise. So there will be no on-campus examination. It will be a remote exam only. The examination dates are on TOM Online already, and the examination registration is open already. The end term will take place on Monday, August the 2nd. Unfortunately, the end term will start at 8 o'clock in the morning. The time for the retake is a little nicer. So if you prefer that, of course, you're free to just do the retake. That will be on Tuesday, October 5th, 11:30. Both will, of course, last 90 minutes. The retake will probably also be a one-time remote exercise. We'll make a final decision sometime in the semester break before exam registration starts. As always, changes are possible depending on the circumstances, so please monitor TOM Online. And of course, I'll also make an announcement on Moodle once we have news for you concerning the examinations. Very quick overview of the examination rules. Basically, things are going to be the same as in the last semester, as in Math 1. So if you've participated there, nothing new for you. If not, as a quick overview, the examination time will be 90 minutes. So working time will be 90 minutes. You'll have an additional 15 minutes to print, if necessary, to scan and to upload your solutions. We will not be able to accept any late submission. So there's absolutely no grace period. The remote exercise will be open book, but of course, communication of any kind is strictly forbidden, and the exam will contain randomized elements. Also, there is a mandatory code of conduct that you have to submit before the examination takes place. So in particular, you're allowed to use books, notes, exercise sheets, the solutions that we provide. You're allowed to watch the videos during the exam if you want to. You're allowed to use a calculator. You're not allowed to communicate or to work in groups of any kind. My recommendation is that you still prepare a cheat sheet, preferably just one page, A4 page, where you write down all the important results, all the important procedures, everything that you think is important. And if possible, try to work with that cheat sheet during exam preparation as well, so that you know where to find things that you might need. As last semester, if we discover any cheating, then this will mean an immediate fail, so grade of 5.0. And also, as another consequence, you will only have one more retake opportunity for this exam if you're being caught cheating. And if you also fail that, that would mean the termination of your study program. In particular, if you submit a solution for the wrong problem, remember there are random elements that will be counted as cheating. And also if we discover obviously copied solutions, that's also a case of cheating. Okay, I'll have more details for those who haven't done an online submission with me yet in the next week. And of course, there'll also be practice opportunities for those who haven't done this yet. We'll again use the TOM exam submission platform. So in case you've been there last semester and you've taken part in the examination, basically nothing will change for you. Okay, that's all about the examination for now. Any immediate questions about that before we start with the exercise sheet?
So there's a couple. Will the retake again be much harder?
I'm not discussing whether retake was harder last time, but again, my answer is not in my opinion.
And then there's one question: how many exercise sheets will there be until the exam?
I haven't counted the weeks yet, to be honest. I'll do that until next time.
normally around 13 weeks.
Yeah,
old.
something like that. 13, maybe 4. Yeah, I guess 13, probably.
Okay. And then they ask if they will get some exam from the last year.
I can upload last year's exams if you want to. Sure.
Okay, and then
I'll do that sometime this week.
okay, and then the last one I see is what about the quizzes? Do we have results there yet?
Unfortunately, no, I haven't gotten feedback from my quiz master yet. I'll have to ask him again. I'll post a message on that to the Moodle forum sometime this week, whenever I have an update.
Okay, that's what I can see for now.
Okay, good. So let's start with sheet 7 then. So here's a quick look at sheet 7. There's 4 problems today, so quite a lot of work to do. Let's start right away with problem C71. There's a function defined on R2, defined like this. So basically that's a multivariate polynomial. And we want to compute the normalized search direction for gradient descent step at a given point, 1, 1. So it's going to be C71. Oops. Okay, so again, our function is f of x1, x2 is equal to x1 minus 2 squared, x2 squared, plus 2x1 squared, 2 minus x2 squared. And we want to do a gradient descent for that function. So the idea of gradient descent is simply to follow the direction of the negative gradient because we want to minimize. So the negative gradient is the direction of steepest local descent. So we're following that direction for a little bit and hopefully get a descent in the function value that way. And we just repeat that procedure until we're satisfied. And that would usually mean the gradient is either 0 or at least close to 0. So hopefully we would have found a local minimum that way. So for the search direction, basically what we need is the negative gradient, or more precisely, the normalized negative gradient. So that's what we are going to compute. We're going to compute minus the gradient of f at the point x0. And we're going to normalize that unless, of course, that gradient is 0. So first thing we do is we compute the gradient, general gradient. So nabla f of x1, x2. So let's first do the partial derivative of that function with respect to x1. We have an x1 here in that term. So to differentiate that means we get 2 times x1 minus 2. Then we have to multiply with the derivative of this function. That would simply be 1. And then, of course, we keep this here because differentiating with respect to x1 means every x2 term is treated as a constant. So just keep that. For the second term, the x1 occurs here. And differentiating that yields a 2 times x1. So together with the 2 that's already there, we get 4x1. And again, we just keep the rest. Okay, so that's the partial derivative with respect to x1. And now for the partial derivative with respect to x2, same thing. Now we need to differentiate that term here first. So we get 2x1 minus 2 squared x2. And here the x2 term is here. So in this case, again, we get the 2 here. So that will be a total of 4. We just keep the x1 squared. And we have 2 minus x2. And then again, we have to multiply with the derivative of the inner function, and that is now -1. So we multiply that thing by -1, and that's the same thing as changing this plus into a minus here, right? Let me do this in a color so that you can all notice what I did here. So this needs to be a minus, and that's the gradient. And now, of course, at the point x0 is 1, 1. We get the gradient by just substituting 1 for both x1 and x2. And if we do that, we get, let's see, we get 2 times -1 times 1 plus 4 times 1 squared. And here we get 2 times -1 squared times 1 minus 4 times 1 squared times 1 squared. So that is, let's see, -2 plus 4, that's 2. And here we get 2 minus 4, that's -2. Okay, so that is the gradient. And now remember, we need the negative gradient and we need it normalized. So let's compute the norm. That is the square root of 2 squared plus -2 squared. Okay, so what we get is 4 plus 4, that's the square root of 8, or 2 times the square root of 2. So our normalized search direction V is going to be the negative gradient divided by 2 times the square root of 2. So that is 1 over the square root of 2 times -1, 1. Right, taking the negative of that, and I cancel out a 2 here. So only this, only this square root of 2 here is what remains. Good. So that's the search direction that we wanted here. Questions?
There's one question about when they need to normalize this vector and when they don't. And if you can comment on that.
So generally, you'll usually normalize. Of course, basically the step size selection kind of depends on that. And if the step size selection is independent of the length of the vector, then of course you don't have to normalize before. And basically we had 2 procedures here. And one was a line search. So that means we take that search direction, and along the line given by that search direction, we are looking for the minimum. And of course, that criterion only depends on the direction itself and not on the length of the gradient or the negative gradient. So that means if you do in line search anyway, then you don't have to normalize your search direction. You can, in which case you just get a different step size. Yeah, but the result in the end, the point that you get will be the same. On the other hand, if you're using a heuristic approach, like the second criterion that we did here, then of course the length of the search direction will mean you'll get different results. So in that case, in the procedure as we discussed it, you would normalize. Again, that's not strictly necessary. The results will be different if you don't do that in this case.
And then there is another question. Would this procedure also work on a Taylor approximation? I'm not 100% sure what's meant.
Not quite sure what you're trying to get with the Taylor process. So basically what this gradient descent does is it kind of uses a Taylor approximation of degree 1, if you want to. So you could interpret that as doing a Taylor approximation of degree 1 and then minimizing that. That would at least be the case if you are using exact line search. Then that's pretty much the same thing.
Okay.
If that is not an answer to your question, then please specify what you actually mean.
And that's what I see for now. So
good. So let's go for C72 then. So that is about the other procedure, the other numerical method that we discussed for determining, hopefully determining local minima of a function. Again, we have a real valued function of two variables. Now that function is simply the sine of x1 times x2. What we're doing here in this problem is we're using Newton's method. And Newton's method is kind of an extension of gradient descent. So I said before that gradient descent, or at least a special case, can be interpreted as doing a Taylor approximation of degree 1 and then minimizing that. Newton's method is doing a Taylor approximation of degree 2 and then minimizing that. The one difference to gradient descent is that there is no step size involved with Newton's method usually. So usually you do this approximation, you jump right to the minimum, and then that is your next point, right? So no step size selection here. Of course, determining the minimum of a quadratic approximation is usually harder than that of a linear approximation. So that will be more work, but hopefully it might also be quicker. So let's see what we have here. So part A, compute the gradient and the Hessian. And of course, if you want to do a quadratic Taylor approximation, that's what you need, the gradient and the Hessian and the function value. So we'll start with that. As for the gradient, so differentiating that expression with respect to x1, we always have to differentiate the sine, and the derivative of the sine is the cosine. And then we have to multiply the result by the derivative of the inner function. That here is the inner function. And differentiating that with respect to x1 just yields x2. So multiply that by x2. And of course, the derivative for x2 is almost the same. It's just the derivative of the inner function that's different. If we differentiate that with respect to x2, then we get x1. Okay, so that is the gradient. And for the Hessian, we just take the gradient and differentiate again. Let's first take that first row here, differentiate that with respect to x1. x1 appears here. So what we get is the derivative of the cosine, that would be the negative sign. So we get something like minus sine of x1 times x2. Then we multiply by the derivative of the inner function, x1, x2. Again, that's x2. And we still have that x2 here. So together with the one that we get from the differentiation, that's an x2 squared. Okay, so that's the first entry of our Hessian. For the second entry, let's do that one here next. So again, we need to differentiate that function here. This time with respect to x2. x2 appears here and here, so we need to use product rule for that. So if you first differentiate that here, we just get that cosine. So that's cosine of x1 times x2. And then we differentiate that part here. Again, differentiating the cosine yields a negative sign. So we get something like minus this first x2. Now simply stays in place. And we get minus sine x1, x2. And differentiating the inner function, x1, x2. that yields an x1. So write that in front here. And that's the result that we get. Okay, so that's the partial derivatives of that first function here. And now for the second one. Differentiating that with respect to x1 works basically the same way we just did. x1 appears here and here. So we need to use product rule again. And we get cosine x1, x2 minus x2, x1 sine of x1, x2. It's not nice. And differentiating that with respect to x2, well, x2 only appears here, this one here. So what we get is minus the sine times x1. And again, we differentiate the inner function with respect to x2. That yields another x1. So we get x1 minus x1 squared sine of x1, x2. And let me see if I can rewrite that a little so that this is a little bit more clear. So that's the first entry here. That is the first entry here. Yeah, it's better. Okay, so that's the Hessian that we get. Part B, write down Newton's equation for a given starting point. That starting point is x0 equals pi 1. And well, Newton's equation, that's basically what you have to know here, is given. The idea is to take that quadratic model, the Taylor approximation of degree 2, and minimize that. And of course, basically what you do is you obtain a stationary point. So you differentiate that Taylor approximation, you compute its gradient, and you're looking for a point that has a gradient of 0. That's the stationary point of the Taylor approximation. And if you do that, you obtain Newton's equation to get you a search direction, so to say. And that equation is, well, you take the Hessian at the current point, x0, times v. V is the search direction that we are going to determine. And that needs to be equal to the negative gradient. Yeah, again, you get that by just solving the equation. Gradient of the Taylor polynomial is 0. So we have the Hessian, we have the gradient, so we can just compute those at the given point, and then we get an equation for the v, and that's going to be the Newton step direction. So in particular, here we have the gradient at pi and 1. Let's have a look at that gradient here, up here. So x1 is pi, x2 is 1. So we get x1 times x2, that's simply pi. So what we get is the cosine of pi, or 1 times the cosine of pi to be more precise, and pi times the cosine of pi. Another cosine of pi is -1. So that's a -1 here and a minus pi here. And for the Hessian, we also just substitute our point. So let's see, in this case, we have the sine. So it's always the sine of x1, x2. x1, x2 again is pi. So we get sines of pi, sorry. So here we have minus x2 squared, that's 1 squared, sine of pi, oh, -1, sorry. Here we have cosine of pi minus pi times sine of pi. Same expression here. And then down here, we get minus x1 squared. So that's minus pi squared sine of pi. And now computing the result, again, the cosine of pi is -1. The sine of pi is 0. So this here will become 0. This will become 0. These terms will become 0. So we're left with cosine pi and cosine pi here, and that's -1. So what we get is 0, -1, -1, 0. And that means Newton's equation will be the equation we've written it down here. Hessian times v equals the negative gradient. So what we need to do is we have this Hessian here, 0, -1, -1, 0 times v1, v2 equals the negative gradient, and the gradient is -1 minus pi. So the negative gradient is just 1 pi. Oops. Okay, so this is Newton's equation for this particular function and that particular point x0. Questions so far?
So I have one that also came up after C, like 7.1. I think it still makes sense now. So why do they need this approximation method? Why can't they just solve like usual for the minima?
Because it might be hard. So what you do is you compute the gradient, you find its stationary points. And you will have noticed that the gradient, if the function is not very simple, the gradient is also not very simple usually. So take this here, sine function, the gradient looks like that already. Now determining the stationary points of that might still be feasible, but it doesn't look that easy, right? Or if you have polynomials of higher degree, then of course the gradient will still be a polynomial of higher degree. Imagine solving a system of polynomials of 7th degree for its roots. You will probably not have a good time doing that. So the functions that appear in practice are often more complicated than the ones that we have here. And that means usually you can't use these analytical methods. What you need is methods that can still deal with these more complex functions. Of course, you wouldn't expect them to give you the correct result right away. So meaning if the result is a root of something in several coordinates, then probably you won't get that analytically. But you might get an approximation. And in practice, that's often what you're looking for. Yeah, you're willing to settle for a point that is close to the minimum if you can actually find a way to compute it. And that's why we need these numerical methods. So we're trying to approximate local minima or local maxima, of course, for functions that are too complex to treat them analytically. That should hopefully answer it.
Yes.
Anything else?
Not so far, no.
Good. So part C, we're now doing one actual Newton step to compute the next iterate in this procedure. So that's part C here. Now, of course, to do that, we first need to compute the actual search direction. Up to this point, we have only written down the equation that we need to solve. No, we need to solve it. The solution in this case is thankfully very simple, because basically this first line here is minus v2 equals 1. So from B, we get minus v2 equals 1. And the second line here is minus v1 equals pi. So two completely independent equations that we can solve right away. And that means our V, consisting of v1 and v2, is going to be minus pi and minus 1. So that's the Newton step here. And remember, we get x1 by simply taking x0 and adding that Newton step. Pretty much the same as in gradient search. In gradient search, you would have some step size here before that search direction. In Newton's method, the step size is always 1. So x0 was, what was x0? Do we have that? Oh yeah, here, pi1. Right. And v is minus pi minus 1. So the result is very nice. x1 is the origin. So Newton step yields the origin here. So that's part C, basically. And part D then asks, is the new iterate already a global minimum? So have we arrived at what we wanted to? And what to do that, you could have first, of course, try to check the gradient. We have computed the general gradient before. So where was that? Here it is. So if we substitute 0 and 0 for x1 and x2, then of course we get 0 times something and 0 times something. So the gradient will be 0, 0. So undoubtedly that is a stationary point. Now let's see if we can find out what type it is. So if we look at the Hessian here, what will that be? HF. Here is our Hessian. So again, substituting 0 and 0, that will yield 0 times that sign, cosine minus 0, cosine minus 0, and again 0. So the only entry that really remains is this cosine of 0. So what we get is for the Hessian a 0, cosine of 0 minus 0, same here, and a 0. The cosine of 0 is 1. So that means what we get is this matrix here. And as you can see, the determinant of that first leading principal minor here, so that is 0. That means this matrix is not positive definite. And it's not negative definite either. So the criteria that we have for determining the type of local extrema doesn't really help in this case, right? We don't know whether there is a minimum or a maximum or maybe something else. So we have to employ other methods. And of course here, thankfully, the function is simple enough so that we can still do that. Remember our function, f of x, x1, x2, was simply the sine of x1, x2. Now at the point 0, we established that already. We have sine of 0, and that is 0. So our current function value is 0. On the other hand, if we compute the function value at the point that we started at, pi and 1, let's compare x1 to the actual starting point. Well, what do we get here? We get a sine of pi times 1. So sine of pi is also 0. So at least the current point is not worse than the one we started with, but it's also not better. So not great progress so far. That might, of course, mean that no progress is possible. But I mean, if we're looking at that function here, we'll basically have a sine. And we know that the sine also takes on negative values. So the question is, can we find a combination of x1, x2 such that this takes on a negative value? And that would prove that this here is not a minimum. And of course, that is possible. For example, if you want the sine to be negative, quick sketch, that's what the sine looks like. All right, so here's pi. let's say you want this point here where it's -1, that would be 3 pi over 2. So for example, we could take 3 pi for x1 and 1 over 2 for x2. Then the function would be the sine of 3 pi over 2, and that is -1. Strictly less than 0. So obviously, the current point x1 is not a global optimum. Right? So that means if the criteria that you have don't really help you with determining local conditions, and the question is for global conditions anyway, then maybe have a good sharp look at the function and see if you know anything about that. And that often helps, and that might even be quicker than having a look at these other criteria. Okay, so it's not a global optimum, and actually Newton's method hasn't made a lot of progress here. Of course, it might make some more progress in the next steps if we can get it to do that. Yeah. Any questions so far?
So there is one question about how do they know which method to use? So will it be given in the task typically, or will they also have to?
So usually the method that you need to choose is given in the tasks. If you really encounter a problem like that in practice, the answer is usually neither of those methods is good enough. Please ask a professional. So both of these methods are important building blocks for more sophisticated and more reliable methods. That's why it's still helpful to know about these. But if you actually want to solve problems where people's lives or monies depends on, then you probably wouldn't use either.
Okay, that was the one question I have.
Okay, let's go on with 7.3 then. Okay, 7.3, this one discusses Taylor polynomials. So here we have a function f of x1, x2 equals e to the power x1 squared times x2 plus cosine of pi x1, x2. And the task is to determine a tangential plane to the graph at the point 1, -1 in a specific form. So we have this point, let's call it x star, 1, -1. And basically a tangential plane is the same thing as an affine approximation. So what we're looking for is the Taylor polynomial of degree 1. At that point x star. So the question could also have been phrased in that way: determine the Taylor polynomial T1. So to do that, what we need is the function value and the gradient, or its value at that point here. So let's start with the function value, f of 1 and -1. That is, let's see, we have e to the power of 1 squared times -1. So that's a -1 plus the cosine of minus pi. And that would be -1, right? So that's e to the -1 -1. For the gradient, so if we differentiate that function with respect to x1, two independent terms here. So let's start with that one here. That would be the e function times the derivative of that inner function. So we get, right, that inner function derivative first, 2x1, x2 times the exponential function. And then here we have the derivative of the cosine, that is the negative sign, times the derivative of the inner function again. The derivative of this here is pi x2. So we get minus pi x2 times sine of pi x1, x2. And differentiating with respect to x2 works similarly. So again, this one here first. The derivative of the inner function is now x1 squared. And again, we keep this exponential term here. Again, we get the negative sign here as the derivative of the outer function. And for the inner function, we get pi x1. So that's minus pi x1 sine of pi x1, x2. Right, and here you have a nice example of a gradient where it might not be that easy to find out about the stationary points. And I'm not even talking about the Hessian matrix. So what we need in this case is the gradient value at the specific point x star, so 1 minus 1. And if we compute that, let's see, what we get is, so x1 times x2 is minus 1, so we get minus 2 here, minus 2. E to the power of 1 squared times minus 1, so e to the minus 1. Similarly here for that second part, it's e to the minus 1 times 1 squared. And that last part here, so here we have x1 times x2, that's minus 1. So we get a sine of minus pi times minus pi here. So that's plus pi sine of minus pi. And here we get pi times 1. So that's minus pi sine of minus pi. And of course, the sine of minus pi is the same as the sine of pi. So that's 0 once again. And we are left with only these exponential terms here. Right, so that's our gradient at the point in question. And now we're ready to compute the Taylor polynomial. So T1f of x at the point 1 minus 1. That is simply f at the point 1 minus 1 plus the gradient of f at the point 1 minus 1 transposed times x minus x star, and x star is 1 minus 1. And remember, x is two-dimensional, so that's x1, x2, that vector here, right? So that's what we get for the Taylor approximation. The function value was e to the minus 1 minus 1. Computed that right here. That gradient here, that was, let's take out the e to the minus 1 to make things a little nicer. And then we have minus 2 and 1 transposed, and here we have x1 minus 1 and x2 plus 1. So what we get is e to the minus 1 plus e to the minus 1. And then we have minus 2 times x1 minus 1 plus x2 plus 1. Right. And now the specific form that is asked for in this problem is we want to write the Taylor polynomial in, let's see if I can get you that here, in this form here. So I want all the x's on one side and a constant on the other side. So basically normal form. And of course, the value of that Taylor polynomial here, that's the third coordinate of the plane that we have, the tangential plane that we're looking for. Right, so here's x1, x2, and that t of that is our x3 of the plane, the function value. So basically what we have to do is we just need to bring that into the right form and collect the terms as necessary. So let's try to do that. So what we get here is x3 equals e to the minus 1 plus, let's collect that right away, 2 to the e, 2 times e to the minus 1, x1 minus 1, plus e to the minus 1, x2 plus 1. And now we need to collect all the x1s and all the x2s and all the x3s. So the x1s we have are here with this factor. And if we take that to the left, we get a 2 e to the minus 1 x1. Then we have for the x2s, it's only this factor here. And again, taking that to the left yields minus e to the minus 1 x2. Then we have this x3 here that is already on the left. So it's plus x3. And all the rest is constant. So we leave that on the right-hand side. So that rest is these two terms here, of course. E to the minus 1. Then this one here. So that's plus 2e to the minus 1. And one more here. Plus e to the minus 1. So what we end up with is 4e to the minus 1 minus 1. And that would be the beta that we're looking for, the constant, whereas these terms here are our alphas, right? So that would be alpha 2, that would be alpha 1, and alpha 3 is just a 1. And of course, if you multiply that by any factor that's not 0, you also get a valid solution, and any of those solutions would have been fine. As you might have guessed, this was actually an exam problem. Okay, questions?
So I have one from before. When a determinant of the Hessian is 0, can we conclude that this is a saddle point? Further computation?
So for a saddle point, the condition is there need to be directions, vectors, where the function increases, and there need to be vectors where the directions where the function decreases. Yeah, I need to get both. And if the determinant is 0, well, it could also just stay constant, or it could just be very, very flat and then increase, or just flat and then decrease, right? So situations in one dimension, you know, those situations like something like that here, that could happen. What we actually need is a situation like that. So a determinant of 0 doesn't give you anything. Everything can happen.
Yeah, that was it.
That was it. Great. So we will almost be on time. Wonderful. Let's start with C74 then. So C74, again, a function, and this time we're going to determine stationary points of that function here. And we're going to determine whether they are local minima, local maxima, saddle points, or yeah, maybe something completely different, whatever that would be. So our function first, f of x1, x2, that's again a polynomial. So x1 times x1 squared minus 3 plus x1 minus 2x2 squared. And let's first determine the gradient to get the stationary points here. So for the gradient, this first term here, that could easily be rewritten as that's x1 to the third minus 3x1, right? So let's differentiate that with respect to x1. And what we get is 3x1 squared minus 3. And for this term here, we differentiate this outer function here first. So that's plus 2 x1 minus 2x2, and then we multiply by the derivative of the inner function, and taking the derivative with respect to x1 is just 1. Okay, so that's the first part of our gradient. For the second part, differentiating with respect to x2, there's no x2 in that first part here, so that just becomes 0. So we only have to consider this one. And again, that's outer function first, 2x1 minus 2x2. And then differentiating that with respect to x2, that yields a minus 2. So we get minus 2 times x1 minus 2x2. Okay, so that is the gradient that we get here. And now we need the stationary points of the gradient. So we want that to be 0 and 0. And that yields a nonlinear equation system. Now, first we have 3x1 squared minus 3 plus 2x1 minus 2x2 is 0. And second, we have minus 4x1 minus 2x2 is 0. Thankfully, that second equation is pretty easy to solve for one of the two variables. So if that expression is going to be 0, then this here must be 0. And that means x1 must be equal to 2x2. Now, if we substitute that into the first equation in here, then what we get is, let's see, 3 times 2x2 squared minus 3 plus 2 times 0, right? Remember that here is 0. Same expression is down here. Okay, so that yields, what does it yield? 4x2 squared equals 1, right? Dividing by 3. And that means x2 squared is 1 over 4. So x2 is plus or minus 1 over 2, square root of 1 over 4. So what we get is the following stationary points. Let's call those x1 and x2. For the first, we take x2 to be 1 over 2. And remember, x1 needs to be 2x2. Oops. Here. So that would simply be 1 then. Or the second stationary point that we get is for x2 equals minus 1 over 2. And again, x1 needs to be twice that value, so minus 1. Right, so those are the two stationary points that we get here. Questions so far?
No, I have 2 questions for 7.3, but we do them then at the end, I guess.
Yeah, well, maybe let's finish 7.4 first, right? Okay, and again, as you can see, determining the stationary points is still possible, but it's not really a nice thing. Nothing that you actually wanted to do, right? So B, for each of those points, decide whether they are minima or maxima or saddle points. So what we need to do there is we need to compute the Hessian. Let's again have a look at the gradient here. Let me just copy that so we can use that to compute the Hessian. So that was the gradient. And that means for the Hessian, we get the following. So if we differentiate this first expression here with respect to x1, we get 6x1 here. And a +2 here. And the rest doesn't contain any x1s. If we differentiate that with respect to x2, then the only x2 is here. We have this 2, so that's 2 times minus 2x2, that's minus 4x2. So differentiating that with respect to x2 yields minus 4. Down here, differentiating that with respect to x1, here's the only x1. That's just a minus 2 times 2, so minus 4. And for the x2 term, we have minus 2 times 2 times minus 2. So that's minus 4 times minus 2, that's a +8. So the Hessian looks a little nicer. And that means if we use the points that we've computed above, now the Hessian of the point 1 and 1/2 first, that will be 6 plus 2, that's 8, minus 4, and 8. The rest is constant anyway. And let's also compute the second one right away. So the other point was -1, -1/2. So we get 6 times -1 plus 2, that's -6 plus 2, that's a -4. And again, the rest is constant. Now let's see if we can find out something about the definiteness here. So you can see this here is positive, right? So that could still be a positive definite matrix. And now if we compute the determinant of that whole matrix here, then we get 8 times 8, that's 64, minus 4 times 4, that's 16. So that's a positive number too, right? And that means these two, this result and this result, that means this matrix 8 minus 4 minus 4, 8 is positive definite. And thus the corresponding point here, x1 equals 1 and 1/2, is a local minimum. So that settles the first. For the second one, we have a negative entry here. So that means that matrix cannot be positive definite anymore. It could still be negative definite. And remember, for negative definite, the leading principal minors have to alternate, starting with a negative value. So that means the determinant would have to be negative. So if we compute that, that was the matrix minus 4, minus 4, minus 4, and 8. Now, if you compute that, what we get is minus 4 times 8 is minus 32. Minus 4 times 4, that's minus 16. So that's negative, not positive. So that means the determinants do not alternate. So the matrix is not negative determinant, not negative definite, and also not positive definite, of course. Right, so it's not positive definite, and it's not negative definite either. It is in fact indefinite. So we have negative values only. And that means we could find vectors in both directions. So vectors that will get a positive result and vectors that will get a negative result. This matrix is an indefinite one. Okay, so that means our point x2 is in fact a saddle point. Okay, so we've classified both local optima. One is a local minimum, the other is not an optimum at all. It's a saddle point. And that means from that point, we can decrease or increase the function depending on the direction that we're moving. So questions on that one?
I still don't see.
Okay.
Okay.
Or of course, we could discuss that 7.3 question.
Maybe we do that, and then maybe there will be more questions popping in for this one.
Yeah.
So in 7.3, can you please explain again why x3 is equal to the Taylor polynomial T1?
Okay, so what we're doing, we want to determine the tangential plane. That means we want to determine a function that approximates, that is an affine approximation to the function at the given point, right? So where's my, here it is. So if that was one-dimensional, I'd have an easier time at drawing that. So imagine we talk about a one-dimensional function. The principle is the same. So we have a function like this, for example, and let's say this here is the point in question. So we're looking for an affine approximation at that point. And that approximation would look like this, basically, right? So this is the Taylor polynomial of order 1. And that means, well, the function values of that Taylor polynomial define the x2 values here, right? The height above this x1 axis of this function. So if this is the Taylor polynomial T1f, this is f, then what I would do is the, say we label this y and x. Then those green y values would correspond to T1f at any given x value for the Taylor polynomial at x star. So this point here is, that is my x star, right? So it means the Taylor polynomial gives you the function value that corresponds to any point around x star. The principle is the same now. We have this function here that depends on 2 variables, not just one. So the Taylor polynomial will also depend on 2 variables, and it will give you an approximative function value. So what we're looking for is the function determined this way, and the function values for any given input x are these here, right? And if you want to do a plot of such a function, what we do is we plot the points given by x1, x2, and the function value. And that function value is our third coordinate. And that's why I'm saying this here is my x3. That's the third coordinate I need. And that corresponds to the function value of this affine approximation. I hope that answers the question.
And if you still find it hard to visualize, you can Google tangent plane, and I'm sure you'll see many examples.
Right.
In 3 dimensions. And then there's another question. So could you explain how you came up with the alpha and beta arrangement in the same exercise?
So basically, let's have a look at the problem statement once again. Basically, the problem statement asks for a representation in that form here. So the coefficients of x1 are alpha 1, those of x2 are alpha 2, those of x3 are alpha 3, and the constant is called beta. Right. So if I wanted to name those or give values to those constants here, what I do is I take this expression x3 equals this. Right, that's what I did here. And then I just rearrange it so that all the x's end up on one side. I chose the left side, but that's totally deliberate. Right, so that's what happens here. All the x's are on the left side. All the constant values are on the right side. And then, of course, I just have to look at what constant is before the x1. That's going to be my alpha 1. Right, this one here. What constant is before x2? That's going to be my alpha 2, which is before x3. That's my alpha 3. And the constants are the beta. That's basically all.
Okay.
The only reason for that formulation, by the way, was that in the exam, there were boxes where you had to enter your values of alpha 1, 2, 3, and beta. That's why they got names.
But a good takeaway is read the question again if you're confused.
Yeah. It's always a good idea to read the question thoroughly.
So the last question I see about 7.4 again is, can we conclude that the matrix is indefinite if the matrix is neither positive definite nor negative definite and the determinant is not 0? It sounds correct to me.
That sounds correct. Yeah. So if you don't get, basically, if you either get alternating values that start with a negative, that start with positive, or if you get non-alternating values that start with negative, then you'll have an indefinite matrix, yeah, or at least one of those. So you need to have, you might get zeros too, but at least one of these things needs to happen if you exclude the zeros somehow.
And then there are no more questions. There was one that maybe we should mention. So on Thursday, it's a holiday, so there will be no tutorials. And
also no Q&A.
Right. And they wondered if they could get the like suggested solutions a bit earlier, like the last time they had a holiday on a Thursday.
Yes, I'll try to put them up probably later today or early tomorrow morning, depending on how much other work comes up today.
Okay, then I don't see anything more. I guess we're done.
Okay, wonderful. So thanks a lot. Have a nice holiday this Thursday. And I hope I'll see you next week then. And thanks to Aline for moderating.